Hello and welcome back to Precalculus. Today we are going to talk about section 2.3 on polynomial functions and their graphs. So you learned a couple of functions that belong to this category already. What you know so far, hopefully, right, is the constant function, which is y equals c. That is going to be a horizontal line through C. It's called constant function because no matter what x you use as the input, the output is always the same value, in this case C. So if that number is, let's say, 2, it's always 2. If the number is 3, it's always 3, and so on. Linear function, which you guys know as y equal mx plus b, is the next one in line. And you know that that's the straight line, right, that has the b-intercept, right, which is a y-intercept. It goes through b, and it has the positive slope, negative slope. You know, to find the slope, right, we reviewed that last chapter. And the one that we studied last class, which is the quadratic function. And I'm going to write the form that it's easy for graphing, the x minus h squared plus k, which gives us that u-shape, what we call parabola. So these are the three functions which you guys are used to and know so far. But what about x to the 7 and x to 35th power and all of that stuff? Can we have all of those? And the answer is yes, right? When we write the formula, right, the general formula for everything, then for all polynomials, they have to account for all of these guys plus more. Actually, you know what? Now that I think about it, I'll put the other form as well because it's going to be easier to see it when I write the polynomial. All right, so in general, what do we have? Polynomial p of x is given by a0 plus a1x plus a2x squared plus a3x cubed plus dot 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 plus an x to the n. What you see here is the general case for any polynomial. An ability to read and understand this formula already tells you a lot about things. So, what do you have here? First of all, we look and understand that this would add as many terms as we want, but the last term here listed definitely says that every polynomial is finite. So you can have 3 terms, 10 terms, or a million terms, but it has to be a finite number of terms. You cannot say, oh, and it goes on forever, because it doesn't. Now, even though this guy is listed last, this is what it's called a leading term, because that's the one with the largest exponent. And if that has the largest exponent, we know that's a leading term, and we know that its coefficient an is a leading coefficient. So we're going to write this again, but well, actually no, we can write it there, leading term, and then an is the leading coefficient. So we have so that term has to exist, and it determines what we also call the order of the polynomial. So the leading term has a lot of stuff in it, right? So that's the leading term. So we can put a line there. Then that's the leading coefficient. And then we can also say order of the polynomial. Actually, just say order equals exponent. So clearly, the quadratic function is going to be order 2 because the highest exponent you have from x squared is 2. We'll have the examples. This is more of a theoretical talk now. Now let's examine what we have here in this polynomial. If I just use the first term and kick everything else out, you have your y equals c, right? We know that p of x or f of x or whatever you want to call it, we call it p of x for polynomial, right, function. But you can put f of x there, you can just put y, whatever. So if you just keep the first term, that's technically your y equals c. If you keep the first two terms and you throw everything else, you have y equal mx plus b. See, this is mx plus b. So what you have here is then quadratic, and then the cubic with x cubed, and then the fourth power quadric, and the fifth power. We don't have names after that for a specific reason. Quadric is the largest. The fifth power is just fifth, and then sixth, and then seventh. I mean, people do come with, some. You might find, if you dig deep enough, you're gonna find, and no one cares. Like it doesn't catch up because, and we'll see the reason in 2.5, right? You just can't calculate zeros of those um, using formulas and things. So we just say whatever, right? The first five, which is constant, and then you have a linear, quadratic, cubic, and quadric, right? So it's five of them. The first five, going up to the fourth power, they have names because we have not just a lot of application for them, but we also know more about them. And when you hit 5 and 6 and 7 and so on, the hell breaks loose, and it's just terrible. But we'll see that when we get there, right? So now we want to understand that as you drop these terms, right, you have the constant, then linear, then quadratic, then cubic, and this particular definition up there shows all of the polynomials, right, that you have, and then you pick what you need. So we can now write examples of this. Let's say you have an example which says f of x equals 3x to the fourth minus 6x squared plus x minus 10, right? Okay, we're looking at this. We know it's a polynomial. And why is it a polynomial? Well, the key aspect of a polynomial is this x to the n. X to the n, and n is the integer. It's a counting integer. So you're not going to have a fraction over here or a decimal, right? That it's not an integer value, right? You can write the fraction as the integer. 7 over 1 is 7, right? But we don't. We just put 7. So when you have this polynomial, it's very important for each one of these variable terms, right, to have x to the n. So we have x to the 4, x squared, and x to the first power, right? So this x is actually raised to the first power. We don't write it, but that's what it is. So now, what do I know about this? What do I know immediately about this polynomial? When I know it's a fourth order, right? I know that the leading term is the 3x to the fourth because that's the highest, right, term with the highest exponent in it. And then I also know leading coefficient, which is 3. And this will play a crucial role in our ability to sketch graphs. Not to get them to the goriest, tiniest detail, but ability to take these graphs and just put the graph, sketch the graph, so we just know the shape, and we'll see when we get there. So now the polynomial is always this combination of terms, right? In this case, you have 1, 2, 3, 4 terms, right? Terms are separated. We know that from algebra. Terms are separated by addition and subtraction. Terms are held together or glued together by constants and multiplication and division, which consists of a constant and then a variable part. Right? So all of that stuff that you learn in algebra, that still holds, right, to make the basic structure. And now when we know what the polynomial is and we have the definition up there, what a polynomial and what it looks like, we would like to kind of sort them and think about them in a particular way. So let's take a look at a basic polynomial that we know technically everything about. Y equals x squared. So this is a polynomial, right? Where if you want to match it to y equal a0 plus a1 x plus a2 x squared, right? You can immediately say, okay, a0 is 0, a1 is 0, and a2 is 1. And if you have this assignment for these coefficients, right, you will get this from the polynomial up there. So that's just, basic definition, and how basic definition actually gets you to any polynomial, not just x squared, but any polynomial. It's just a game of these constants in front of the variables, right? Which you can, if you have 0, you kill that term, and if you have a number there, then that number multiplies the variable, and you just have that variable. Anyway, what do we have here? Well, we can draw the graph for this because we already know what it looks like. And we are going to take a look at the features of this graph. So what are all of the features that you can possibly imagine over here? Well, one of the features is x-intercept. And that x-intercept is the place where graph goes through or touches x-axis, right? Because it's called x-intercept, right? You're intercepting. So just the wording, right? The English language helps you immediately with the meaning. So for x-intercept, we set y equal to 0 because you want to find when you go through x. So on the elevation of x-axis, y is equal to 0 everywhere. No matter which point you pick on the x-axis, right, the y is always 0 if you are talking about the x-intercept. So no matter, right, if I draw the line x like this and then just have a function snake through it a few times, this is, let's say, a, but it's going to be a comma 0. It's going to be b comma 0. It's going to be c comma 0, right? Because each one of these is on x-axis and the y coordinate is always 0 on x-axis. So it makes sense, right? Common sense, I guess, or whatever, that if you're looking for the x-intercept, you set y to 0. So you're forcing to see if the function cuts through x-axis, right? So set that. And then for the y-intercept, you do the same, right? You set now x equal to 0 because along the side of y, you can have that. Now, one thing here to understand is that polynomials are not all alike, and one thing is guaranteed, that at times you can have at most one y-intercept, right? At most one y-intercept. Well, in case of polynomials, you always have to have a y-intercept. You always have to have one. But we'll see why. But but one thing is guaranteed: you can never have more than one y-intercept. Can anyone tell me why it's impossible to have more than one y-intercept? Why is that guaranteed? We're talking about polynomial function, and I just said you must have a y-intercept, but you can never have two or more y-intercepts. You can only have one. Like Highlanders, right? There can be only one.
It's a rule of the function.
It's the rule of the function. Very good, right? Vertical line test. So if you are looking for two y-intercepts, then they would be for the same x, and then one x gives two, right, or more outputs, and that ruins the function definition. Very, very good. Yes.
Oh, so there has to be one output, correct?
Yes.
Oh, yeah.
So there has to be one output, and because of that we have this situation. Awesome. Awesome. Good. So now when you talk about these polynomials, right? We're looking at this one now. So we'll take a look at the domain, and we see that it's negative infinity to positive infinity. So any value between negative infinity and positive infinity on x-axis can be used. How about range? Well, in this case, the range is including 0, right, and going to positive infinity. So including 0, going to positive infinity. Okay. Is there anything else we need to talk about in this case? No, I mean that's it. You can visually see that this part of the graph is decreasing, the other one is increasing, right? Because the values of y go down and then up, right? But those are little details that we will talk about later. We don't have to talk about it now. All right, cool. So, and we also know that this point over here, right, in this case 0, 0 is a minimum. And we can see that's the lowest point because it has the smallest y value. It's the lowest point on the graph. And then there is no maximum because both of these edges go up forever to positive infinity. So they're not going to settle down to a number so you can say, oh, that's a maximum value, right? Now, all of these things we had from our previous class. There is nothing new here. But we are going to now take a look at y equal, or f of x equals x cubed, which is this squiggle like this. And now we are going to see that your x-intercept is at 0, 0. Your y-intercept is also at 0, 0. You are also going to have the domain, right? You can plug in anything, negative infinity to positive infinity. And our range is also negative infinity to positive infinity because it takes on all of the values for y as well, not just for x, but for y as well. So you can plug in any number and get appropriate right answer when you cube that number. So that is what we have for the cube function. So now I want to compare x squared and x cubed, and apart from x-intercept and y-intercept, which can move, obviously, one thing we see that both have the infinite domain. And if you think about it just a tiny little bit, you immediately realize, hold on, all of the polynomials will have infinite domain because each one of them is x to the n. I can plug in any number and either square it or put the 7th power or 1000 power on it. It doesn't matter. So this kind of helps us realize that for all polynomials, domain is given by negative infinity to positive infinity. So if you have a polynomial, you have the domain to be all infinity of numbers, anything. Range Well, we already seen here between these two examples, range is going to be case-by-case basis, right? Because up there you just have this 0 to infinity, and down here negative infinity to infinity. So when you have that kind of variation, immediately you can't make a general rule, right? Because remember, you do not have exceptions in mathematics, right? You have rule, and that rule has to fit all. Otherwise, you do not waste time writing a rule, because it's a dumb rule if you can have exceptions. Now, I understand that the society is not structured that way, so exceptions to the rule are they're piling up, right? But in case of mathematics, which is why, right, you can't argue with mathematics, you can't argue against mathematics, you can't argue, right? It's there, and it's the ultimate truth, right? You have a rule which says that all polynomials have the domain negative infinity to infinity, and then there is no rule for the domain, because again, you can have different types of these situations. So that's a big part there, which will be used later a lot in calculus and so on. So for all polynomials, domain negative infinity to positive infinity, that's very, very important. Okay, so we got through these basics now, where I kind of should have boxed this as well, because this is also a rule for all functions, not just polynomial. It's going to work for trig as well later on. When you want x-intercept, you set y equal to 0, you solve equations. And if you want the y-intercept, you set x equal to 0, and you solve, right, compute what you have. Now, if I want to find x and y-intercept for f of x equals 4x cubed minus, I don't know, 8, whatever, then we have to go and do those one by one. So y-intercept is easy, because we are supposed to set x equal to 0. Okay, well, that's just f of 0, which is 4 times 0 cubed minus 8, which is negative 8. And you have your, since you set x equal to 0, your coordinate is 0, and f of 0, which is a y value, gives you negative 8. And that's a point which you get to graph on the graph paper and have your y-intercept. Now, x-intercept is set y equal to 0. So that's going to be 0 equals 4x cubed minus 8. Now you have to solve the equation. Now, clearly, it's not always to be easy and a joke like what you see here, right? And as I said, in some cases, it's going to be impossible to do, right? So we have to go and use numerical methods and whatever else calculus would offer later, not now. So I move 8 to the other side. I get 4x cubed equals to 8. Divide by 4 on both sides. Get x cubed equals to 2. And finally get my x equals cube root of 2. Now, there are more solutions than this, but they are in a complex plane, and we kind of don't care about them now because we're terrible people. But yeah, we will discover that if you have a cubic equation, you have to have 3 roots, right? So that's something that it's coming up very, very soon in this course. Anyway, what we are going to have here now is this x intercept of cube root of 2 comma 0, right? And y is equal to 0 because you set y equal to 0. And you have your x-intercept. So x comma y, every point is x comma y. So that's again a point.
You
X and y.
I think you dropped the negative sign.
I didn't. Why?
Well, you divide it by 4.
When you add 8 to the other side, it's a positive, and then 8 divided
He
by 4.
switched
Oh,
sides
oh
around.
no, yeah, I see now. Okay,
All right, cool.
never mind.
All right. That's good. Keep checking, because eventually I am going to mess it up, and I will need that to save. So yeah, keep checking, and yeah, eventually it will happen. It has to. I do way too many of these problems. Sometimes I don't even think about it, and then I just drop it. All right. So now we are out of this algebra part plus the domain part, which is Precalc, and we need to go right into this, what we call a leading term test, which actually gets you into graphing. Now, there is a ton of stuff here, and we kind of have to cover a lot of that stuff at the same time so it starts making sense. So please double and triple focus here, right? So the good old friend of an x to the n, which we called the leading term. Remember, largest exponent, right? Has these two features. It has this leading coefficient, and it also has this exponent. Now, leading coefficient is either going to be smaller or larger than 0. So an can be smaller than 0, or an can be larger than 0. And it cannot be 0, because if you put it 0, it's going to kill the leading term, because 0 times x to the n is just going to kill completely the order of the polynomial, right? If you have a polynomial to be x to the 7 plus 3x to the 6 minus x to the 4 plus blah, 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 whatever, right? That's a 7th degree polynomial, because there is your order, 7th degree, because it has x to the 7. So if you stick a 0 in front, then 0 times this is going to kill that term, and then now you have a 6th degree polynomial. So you can never have an equal to 0, which is why in a definition, and terrible me, I didn't write it, I should have, in a definition, you always have to also state that an can never be 0, right? That's a part of the definition. If you open the book, you'll find it there. So because of that, right, your an, which is a leading coefficient, can either be larger than 0 or smaller than 0. So that's one thing that you have to worry about. And exponent can either be even or odd, right? So those are your two options for the exponent. So exponent is 7 or 8 or 2 or 100, right? So it's going to be even or odd. Now, those are the two things that you absolutely have to know. And when you look at those two, they will tell you which way to draw the function, which is really, really cool, right? You don't know anything about x to the 15th power, but you can still sketch the graph. I think that's really, really cool. Now, before we jump there, let's put this box, which will have 4 cells, and say that, let's actually make the box at 4 cells. So we're going to say that over here you're going to, I mean, we can rearrange this any way we want, but let's say these are your even and it's your odd. Now you know I mean exponent, and this is your a larger than 0 and your a smaller than 0. So what you see here are 4 combinations. The only 4 combinations that you can have. Can't have more than these 4. So now, what do they mean? Well, they help you with something that we call the end behavior of the function, which helps you graph the functions as you go. So where do you pick these values? This should say an, maybe. There we go. You pick them up when you look at your term, leading term. So now, if the exponent is even, and if the coefficient is larger than 0, both ends of your polynomial function will look up. Now, this will depend on, we'll see later, on what the exponent actually is. So if I say even and larger than 0 for an, well, even exponent could be 2, could be 4, could be 6, could be 8, could be 100, could be 500, right? And literally that will determine these oscillations in between, let's say. And if you have an even function, even exponent, sorry, with the negative coefficients, then it looks down, which those of you who studied 1.6 would say, yeah, obviously, because you are changing your an to be negative an, which means you are reflecting on x-axis, so duh, right, with the attitude, which is okay. So yes, all this does is actually reflects it on x-axis because you put the minus in front of the function. That's just the stuff you learned in 1.6, but we put it here just for the sake of completing the chart. Now, if it's odd and larger than 0, one looks up, one looks down with a in between. And as you can see, the whole trend is increasing. So you start with the arrow looking down, and then the other one looks up. And then obviously opposite for this, so it's going to go like this, and it's going to have the BI in between. These are the only 4 possibilities to graph all of the infinity of polynomials, to sketch the graph of all of the infinity of polynomials that you have.
Would a parabola be the top left and a linear line would be the top right?
Very good. Yes, linear line y equal mx plus b has the exponent of 1. That's odd. And when the positive slope looks like that, when you have a negative slope, it's the bottom one.
Gotcha.
Very good. Now I'm going to enrich this with y cubed. We had the graph earlier up there. It looks like this. Well, that fits this description, right? Because I put y cubed, that means there is a positive 1 in front of it, which we never write. So that's a larger than 0. And it's odd exponent because it's cubed. Now, the bottom one, when you put the negative, it's going to look like this. And you would say, oh, yes, it's only a reflection. Yeah, but this is negative y cubed. And you know that this negative is supposed to reflect it on the x-axis. This has to click 100% with everything you learned in 1.6. It cannot exist as separate entities where one is one way and the other one is other way. That was very, very good, yes. What do you have on the left side with even? You have your x squared pointing up and your x squared pointing down, negative x squared pointing down. So that fits as well. I mean, obviously, this is the way the whole polynomial world works, no matter what you come up with. So if you go and you say, well, now I'm going to be obnoxious and ask a question about x to the 17 plus 3x to the 16 minus whatever 10x to the 15, and then you just give me this polynomial with all of these terms, I just ignore everything you said except the first term. You said x to 17. Okay, a is bigger than 0, and 17 is the odd number. Good. Larger than 0 odd number, it fits here. That's all I need to know. I just need to know the leading term, the one with the highest exponent. What is its coefficient, positive or negative, and what is the exponent of the term, right? Technically, the order.
I'm a little confused about what AN represents.
AN represents whatever is the highest term. So when you look at the definition for the polynomial, there we go, you see that we can, what you learned before, mx plus b or a, b, c. When you talk a, b, c, you have 26 letters, right? Where I come from, we have 30 letters. You can pick any culture you want. They're going to have a finite amount of letters. So eventually you're going to run out of letters. So instead of using different letters, A, B, C, D, blah, 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 let's use A0, A1, A2, A3, A4 instead of A, B, C. Because if I go A0, A1, A2 to represent the coefficients, then I can use as many of those as I want because they depend on the number that you can increase as much as you want, where your alphabet runs out to 26 letters. So technically this AN means whatever the exponent is, which is, let's say, x to the fourth, then this becomes a to the fourth over here, because that n is the same as the other n, and it's just the index to tell us that that's a coefficient which is different than a3, different than a2, different than a1, and different than a0, because they can all be different numbers.
So in that example, just a little, if you scroll down just a little bit right below that box, in that example right there, f of x equals 3x to the fourth, the a of n would be 3, 4?
Yes.
Okay.
AN would be, yes, but we would call it A4, right? Because the only reason why we're using AN over here is because we don't know how far we're going to go. And this n can take on any number that we want, which is why we put AN. But as soon as you put a finite polynomial, that AN becomes set in stone. It's A4. There is no AN in a problem, right? AN becomes immediately A and then the subscript.
Okay. Oh, so it won't become 3, 4. It still stays A. It just becomes A4 instead of AN.
Yes, because it's the
Gotcha.
right, because it has to match the exponent. It's just the index to give us like a location of where it goes. So if you take a look at what are explicitly written over here, right? Just ignore everything else. Just look inside the box. You see that a3 is just a coefficient of the x cubed term, and a2 is a coefficient of x squared term. A1, right? So the power always matches. And instead of writing A plus bx plus cx squared plus dx cubed, which I can, right? I would rather write them as A0, A1, A2 because that way I'm not going to run out after 26 terms. I'm not going to run out of letters because the numbers can go as far as I want. So does this help a little bit?
Definitely.
Awesome. So that's what AN is, right? AN is just a counter that the highest term will have as a coefficient. So going back now to our chart over here, right? If I go and I say, all right, so sketch f of x equals negative 6 x to the 5 plus x to the 4 minus 3x squared plus 7x minus 10. The whole thing is blah, 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 because that's the boss. The rest doesn't matter. For a sketch, clearly it matters for the detailed graph of the function, but for a sketch, all of that goes to garbage. You just look at the leading term. Now, what do we learn from the leading term? We learned that the A5 is less than 0. You can just say A, but you can also say A5 because you know that AN x to the n, this has to match. So if you have your x to the 5, this better be A5 in front, like, because they match. So we learned that a5 is less than 0, and we also learned that n equals 5 is odd. Okay, odd less than 0. That's this case. So this function that will go through -10 on the y-axis, because that's very easy to compute the y-intercept, right? If each x is 0, then what you get is -10. So that's going to go down to -10. And then you are going to have some kind of a function, but as you can see, right, this one part is going up, one part is going down, and the function is going to do something in between. We don't know what the function does in between now, but we know that it's going to do some of these things. So that's what we have for sketching the graphs. And obviously you can get better if you know zeros of the graph. And we still have to talk about multiplicities and things, which helps with these bumps, but we're we're not even close to being done here. But before we get there, I hope that you guys had the time, right, to study this graph. Maybe take the picture, your phone or something, and because it's really very convenient to even draw the graphs. Even with the functions, you have no clue what they look like. You can sketch the graph and have some idea of what they look like. Cool. So what now?
Professor,
Yes.
down a little bit, just a tiny bit. I just missed something.
You said you missed something, right? You have a...
Yeah, could you just go down a little
Oh,
bit?
scroll down. I didn't hear that. Is Oh,
yeah,
this
right there.
one. Okay.
Oh, okay, I got it.
Yeah.
All right.
So as I said, right, it doesn't matter which will right. It doesn't matter which way we for now, because is a little sketch, and then we'll add this stuff as we go on. Okay. So time to take a look at graphs in more detail and try and figure things out a little bit more by figuring out what we mentioned before, x and y intercepts. Okay, so let's say you have f of x equals x cubed plus 3x squared minus x minus 3. And the question is graph. Sketch the graph, right? There are certain things that you, even when you do those, what I mentioned, you still can't get exactly everything right. But the sketch is very important and very powerful. So what do we have? I need my y-intercept. Okay, that's always easy, because that's f of 0, right, which is 0 cubed plus 3 times 0 squared minus 0 minus 3. The whole thing is always just descent number, right, because all the other terms have to die because they're all zeros, right? So the y-intercept of -3 is always easy, and you're just going to call it 0, -3, and you're done. It's the x-intercept, which is when you set y equal to 0, which is a problem in many cases. So now you are actually solving equation, and for polynomials, guys, it's always technically just good luck. All right. Factoring is your best friend. Quadratic equations is your best friend, but trust me, we are going to devote 3 lectures to figuring out zero, this being the first one. The algebra cases where you can factor when everything is nice and, you know, the beautiful, yeah, that's this class. The more complicated cases are starting with the next lecture, and then obviously zeros of polynomials at the end. Now, depending on your knowledge of algebra, right, it might be obvious to you that factoring by grouping is the way to go here. And you can group these as x cubed minus x plus 3x squared minus 3 equals 0. And then when you group them, you can kick out an x. You get x squared minus 1. You can kick out 3. And you get your x squared minus 1 again. And now you pull x squared minus 1. You get x plus 3, the leftovers. And finally, factor x minus 1, x plus 1, x plus 3. And then use the zero product rule. Hopefully you remember that one. Zero product rule, which would give you each one of these set to 0. Maybe I should write that product rule just in case. And now x is equal to 1, x is equal to negative 1, x is equal to negative 3. There they are. 3 roots, also known as x-intercepts. 3 roots. So what are the roots? 1, 0, negative 1, 0, and negative 3, 0. By the way, zero product rule was if a times b equals 0, then a equals 0 or b equals 0. Now, you can have a times b times c, you know, how many of these you want. We had 3 in this case. And this is what we have, right? This rule lets us, when we have the situation, right, when you have a product of things equal to 0, that means that you can set each individual factor equal to 0 and solve each individual equation. Now, this is not going to leave anytime soon. You'll have this in every chapter of our book, pretty much, and obviously calculus and so on. So zero product rule and solving equations in this way is very valuable and very frequent. So don't lose the sight of it. I have a lot of information to graph this function. Let's see what I have. Leading term was just x cubed. That tells me that my a is bigger than 0 and my exponent is odd, which gives me the end behavior like this. And I also have the 4 points that I can graph, and then we can snake the function in between them. All right, I have, let's go 2 units as 1 unit. So first rule of engineering, draw big. So what do I have? I have 1, 0. That's this puppy here at 1. I have negative 1, 0. That's this puppy here at negative 1. And negative 3, 0. So these are my 3 x-intercepts. And you see that they are intercepts because the graph will pass through those, hopefully, or bounce off of them, and make the intercept with the x-axis. And then we have the y one, which was negative 3. So that's going to be right here, negative 3 y-intercept. So now I have this behavior. So I get to draw this to the left of the root and draw the other arrow to the right of the other root. So now we need to connect this end with the other end up there, going through all of these points somehow. Well, in this case, this tends to be easy because if I shoot to 3, bend, go through 1, shoot through 1, bend at, let's say, 3, and then shoot this way and connect, there we go, right? So I was able to just start from one side and snake this function through. Let's go again, because we can. I have to start at the left side, and I'm going to follow this and shoot through 3, bend to get through -1, because I have to go through every of these points. It's like, it's the same like connecting the dots, except you're not 3 years old and you don't have to color. There is not much of a work here. So you go down through this, you go up, and that will go forever up. Is this the only way? Well, we don't know the heights of this maximum and minimum. So maybe someone is going to draw this way, pass this, and then go up like that. That's possibility, right? Which is why I say we don't know, right? Can go maybe up and then down and then bounce here and then pass to this one and pass to this one. Like, there are so many ways, which is why it's a sketch. It's not the exact graph. So don't panic, right? Whatever fits through those points, whichever way it fits, it's not guaranteed to have a minimum at this value. I mean, I can use calculus to compute where it is, but as I said, we're doing the sketch, so it doesn't matter. You can't be precise, very precise with these graphs because we don't have enough information in Precalc to do that. So this is one standard problem where you have a function and you're supposed to sketch a graph, and then you say, okay, I could sketch a quick graph, but then I have to use those squiggles. And in some sense, since the factoring was easy and everything went very well, it was reasonably easy to find those roots, right? The x-intercepts. The y-intercept is always the easiest, obviously, so you just plug that in. And there you go, right? So we know now how to find, how to draw this graph. Now, it's not the end of the story, because not every graph goes through the x and y intercepts. I mean, through x intercepts. They have to go to y, but they don't have to go through x. So what do you do with the parabola, right, that goes like this? Well, parabola, you will say, oh, yeah, that's easy because this point here is the vertex and I just have h and k, and if I don't have it, I do completing the square. Okay, yeah, that's your beautiful world of x squared. What are you going to do now? X to the fourth. Your methods don't work anymore, right? And then if you go and you figure out how to do it x to the fourth, my immediate question is x to the sixth, which will take you even longer to figure things out. And then when you're done with that, I have x to the eighth. And I can play this game forever because every time I give you the higher power, it's going to take you insane amount of time to grind through those and try to get anywhere, right? So we are not going to learn, oh, x squared or x to the fourth or whatever. We're going to learn the principle that goes for all of them, which is that chart, right? What goes up, what goes down. Also, in addition to that, we need to be able, if we can, right, to solve for those roots. Because those are x-intercepts, right? And finally, right, we also want to learn these situations where the graph doesn't go through the x-axis or the graph bounces through the x-axis, right? So touching only one spot, or cutting through in two spots. See, so just the x squared, right, with its shifts, can not touch x-axis at all, could touch x-axis once, could cut through it twice. Obviously can't cut 3 times because it's x squared. So x squared is the U shape that never bends back to cut through x-axis one more time. But thinking about this, right, I have the 3 possibilities. And they're all some kind of x squared possibilities. So now we immediately realize that the quadratic formula, which we use to calculate those zeros, will have 3 possibilities for answers. And each one of those is represented now in the picture. So when you go and you say x equals negative b plus minus square root of b squared minus 4ac divided by 2a, okay, when you have this, you can have 3 separate possible answers. This is a 2 distinct real. Then you can have 1 repeated real answer, solution, whatever. And you can have the 2 complex conjugate answers. Well, woohoo, right? They match those graphs up there. You should be able to quickly match it because clearly the middle one is the middle one because that's only 1, right? And then over here you see on the right side that it cuts through the x-axis, which gives 2 real x numbers twice. So if you link them, the top one goes there, the second one goes there, and finally the complex one is there. Oh, so I get complex solutions when the graph doesn't cut through x-axis. Exactly! Because if it cuts through x-axis, then you have real solutions, right? Because those are the real numbers that you see, right? But when it doesn't cut the x-axis, that means your solutions are complex. Now, you've seen, and we talked about it, right? Complex doesn't mean, or imaginary doesn't mean it doesn't exist, because there is a graph, clearly exists. The roots are complex numbers, but still, everything is fine, right? We talked about having unfortunate name. So we really want to see this repeated root here, because look what happened. It bounced off of the x-axis. Aha. So now we actually get to talk about the repeated roots, which lead into what we call multiplicities. And that further helps our graphing. I'm going to come up with already factored problem because I can. Negative 4 x plus 1 squared times x minus 3 graph. See, I have 2 negative 1 roots now. Okay, let's use a zero product rule. We have x plus 1 equal to 0, x equals negative 1, and I'm going to put this in blood, m2 next to it. And this one is x minus 3 equals 0, x equals 3. And I'm going to put this m1 next to it. So What are these? M1, M2, maybe M3, M6? Those are how many of the same roots you have, right, as a solution of your equation. So multiplicity of a root tracks how many copies of the same root we have, right? Because think about it, guys, for this x squared term. If I write this as x plus 1 times x plus 1 and then set each one of these, right, equal to 0, I'll have two of them, right? I just mush them together with this square because it's easier to write and shorter to write. But in all honesty, I have two of those multiplying each other. So I could just set each one independently. One is going to spit out -1. The other one is going to spit out -1. Well, that's what we have. We have two -1 roots. And that's what the M1 and M2 means. You will see M3, M4, meaning that they have that many roots. Now, how does this help the graph? Ooh, this does wonders on the graph. So we have that -1, which is M2 root. I'm still going to write that, M2 root. And we also have x equals 3, which is the M1 root. 1, 2, this is terrible, but the tablet is rocking. I can't do anything here. 3, and that's the M1 root. I also have that my degree is 3. How many x values do I have? I have 2 x values in the first one and this one. That's 3x, right? So that's x cubed. If I have x cubed, I know that's odd. I also have a is -4. So when I put all of those things together, I have a is equal to -4, which is less than 0, and I have n to be 3, which is odd. So what does that mean? Well, that means that the function should have these end behavior like that. So now, I hope you're paying attention on this one because that's going to be tricky. Look. M2, if you look at your M2 from before, see that M2 is a bounce? It's a one repeated real solution, it's a bounce. So, when this side of the graph comes down, it's not going to go through -1. It's going to go bounce off of it because it is M2. It's a multiplicity 2, and it bounces the answers. Then the graph is going to turn through 3 and connect there. So now we learn that these multiplicities also follow the rules of the powers. But we're going to get there. Let me just one more time. If you are not able to connect pieces and you have to invent x-intercepts from thin air, you are doing the graph wrong. You have to check your calculations, you have to check your multiplicities and things like that. There is no way for me to connect this graph if I don't bounce it off at 1. If I shoot straight through and then bring it back to 3, I can't bend back to match the graph at the other arrow. Because I'm not allowed to cross x-axis anymore. I found all of the roots. So I'm not allowed to invent another root over here so I can connect. You're not allowed to do that. So if you are ignoring multiplicities, then you are going to lose the sight that it's actually a bounce over here, because that's what M2 means, a bounce. And then we're going to turn, and M1 means go straight through and then connect. So that's what the M1 means. So now you go and you say, oh, so those are actually following my knowledge of my functions that I have from before. Yes. Here, I'll write this in blood. M1 is a straight through. M2 is a bounce. M3 is a through, but it's going to go through as a cubic. It's going to go through as a cubic like this. So that's your M3. And from there, you're going to go and say, oh, M4. Well, M4 is also going to be a bounce, but it's going to hang around longer, right? Because the M2 just bounces right off. This one kind of hangs around a little bit longer. And you can go with these, right? The M5 is going to be the same as M3, except it's going to hang around even longer. It's going to go like this and hang around longer and go like that. M7, M8, sorry, M7, M9, right? Because they have to be odd ones. So 3, 5, 7, 9, and so on. M, multiplicity, right? How many same roots you have on a pile. So you can snake these through the graph. And again, M2 was a bounce, and M1 at 3 is a straight through. It's like a linear pass through. It just shoots through the. I can shoot that way, I can shoot this way. Doesn't matter. It's just a one shot. So I'm going to give you now a problem to try on your own, and then I'll give you 1 or 2 minutes to try and graph this on your own, and then I am going to work it out so you can check your work. So let's go with 6x minus 1 to the 4, and then x plus 2, and let's just do this for now. This is good enough. What's up, buddy?
So mommy signed me up for Roblox because it didn't work every time. So, and now every time I load into a world, I just have like this random girl skin and stuff. I spawn with somebody that just has a pizza shirt and just like a girl hat. Just it's all girly and there's no boy stuff. Everything is just girl.
Yeah, I can't fix that now, buddy.
And how are you supposed to make my skin again?
Yeah, so we'll have to look at it. I have a class, and I can't do anything now until I.
But Daddy, you can just hurry up, please, because I need you to do it.
Mimi, this is more important. This is where you get your food in life. The game is not as important as this. You have to understand that. You go play Raft. Go play BMG. Go play Train Simulator. Go play literally anything else. You have Minecraft.
Is that your screen?
You have Satisfactory. Yes, I'm streaming on YouTube right now. But the microphone is off. So.
So you're gonna post this on YouTube for your students to see?
Actually, my microphone is not off. All of this stuff is on YouTube now.
So they hear us, both of us?
Yes, I have to delete this part. Go.
Okay.
And please don't interrupt. I have a class. I can't have these conversations right while the students are doing the work. Go. All right. Any luck? Hopefully.
I think I got it. I'm not 100% sure what we're looking for, but I just basically
graph,
did
right?
the last one. Oh, then yeah, I think I got it.
Let's go. So my son actually came in to bother me with the video games. Oh man, they just know. Anyway, so let's go and take a look at this. So my A is equal to 6, which is larger than 0.
It's also even.
Exponent is odd. Yeah,
Oh wait. Oh, I forgot.
Four
I looked at
x's
the
on a
coefficient
pile,
twice.
and then one x over there is all together n equals 5. That's odd. All right, cool. Not a big deal. So what do we have here? We have exponent is going to be odd, and we have the larger than, which means it goes this way and that way for the end behavior. And now we have to deal with our roots. So what are my roots? Roots are going to be x equals 1 with a multiplicity 4, and x equals -2 with multiplicity 1. I hope all of you can mentally set this to 0 and just add 1 and subtract 2 without writing all of the equations in between. I mean, there's nothing to write in between. X minus 1 equals 0. If you want to write the step, it's just, yeah, that's what it is.
Can I ask a quick question?
Yes.
I think I missed where you're getting the multiplicity 4 from. Where's the 4 coming from? I thought that would be multiplicity. Oh, so it's just the exponent that it's coming out of?
Yes, because the fourth has 4 roots, 2 has 2 roots, 3 has 3 roots, right? So it always matches the exponent. So this is the exponent of 1, so multiplicity 1.
Gotcha. And
Awesome.
the number of multiplicity just affects how wide the sketch of the graph is going to be?
Yes, because they're either going through like this, or the cubic one, or they make it wider, right, as it goes. So let's check now. Sketching the graph over here. I'm going to have my, what? X is -2. Right, x is -2. And that's M1, which means the graph is just going to shoot through. And then I have M4 at +1. And I have the behavior. You always draw the behavior to the left of the last point and to the right, right? So you see, right, where I put these arrows, because they need to connect into, right, their end behavior. So everything that is interesting in a graph will happen with these two vertical lines, all the turns and ups and downs and all that. And then after that, it just becomes boring one way going forever. So when I put this M1 and M4 here, I don't need anything else. I'm just looking at that and I say M1 is a straight through, and M4 is a bounce because it's an even, right? And the evens are bounce. So whether it's a skinny bounce or a fat bounce, that depends on the number. Whether it's a 2 or a 4. So this is a 2 bounce, this is a 4 bounce, even fatter for 6 bounce, and so on. So that's the only thing that it is, but it's a bounce. So I know it's going to be, I have to turn back, and it's going to be a wider bounce, and then it's going to go up, and it's going to fix this arrow, put it there on the side, and there we go. So it's a wider bounce. Skinnier bounce for x2, like that. Now, it's not humanly possible. Guys, these are sketches. These are not exact graphs. Because I don't know how tall this bump is. Does it go there? Does it go there? I have no information currently without calculus to give you those answers. So we are going to revisit these problems exactly in calculus and have way more interesting stuff, but we need more tools. Right now, we are connecting these the best we can with the tools we have without use of derivatives and other stuff that is there in calculus. Let's take a look at another example. So I'm going to ask you guys to graph another one of these. say f of x is equal to negative 2 x minus 3 squared and x plus 1 cubed. So let's see what you get in this case. Just let me know, is a less than or larger than 0?
Less than.
Less than. I have a question.
And what's n?
Oh, it's
That
5.
was my question.
How much is n?
I put 5.
Good. Which is odd. I'll help with odd. The first parenthesis has 2 x's. The second parenthesis has 3 x's. That's together 5 x's. That's all it is. Don't make it complicated. Yes.
Professor, for this one, would the bounds depend on which like parentheses has the higher exponent, or would they just both bounce?
One is a 3, so it's a pass-through. The other one is a 2, which is a bounce.
Oh, okay.
Right? Look at it. If you need to take the picture with your phone now, so you can refer to it, or if you took the notes, whatever. But the M3 route that you are going to have is going to be a pass-through. Every odd one is a pass-through. Every even is a bounce. And the number 1, 3, 5, 7 is going to be the fatness, just like 2, 4, 6, 8 is a fatness of it, right? But every single odd one is going to be a pass-through, and every single even one is going to be a bounce. So going back to our problem, right? There is a bounce at 3 and pass-through through negative 1. So with this one goes like this. All right. So now what we're going to have is what? The graph over here, and we have our values. M2, M1, no, M3, M3. And I have this one and this one. So I don't need to see any more problem. I have all of the information that I need to graph right there because I have my M3 and my M2 there. And you can start drawing this from any end. It doesn't matter. So we're going to go down and then make this kind of fatter, right? Pass through. Wide. There we go. And if you go from this side, oh, there's going to be a bounce. And look, they just connect. Woohoo! So here is the cubic pass-through because it's M3, and here is the quadratic bounce because it's M2. This has to click in every single time. If you can't connect them, you are missing an exponent. You counted exponents wrong, so you have these arrows wrong. There are many ways to mess things up, right? You missed the negative, so your A is wrong way, so these are backwards, right? There are, you know, a lot of things to consider, but it's very structured, right? You have the odds are pass-throughs and evens are bounces, and just the number is the width. What I say how fat they are, right? So the width, and that's the end of the story. And I can't make this tricky. It's impossible to make it tricky if you know the three rules technically, right? You have the even m's, odd m's, and the leading term to give you the end behavior. Those are the three things. Those are the only three things you need, and you are done. So now I'm going to read the problem. So these are the ones that I was just making up, right? As I was going through. Now I'm going to actually jump into a homework page here, and pick something from homework. Let's say 57 looks diabolical enough, I guess. F of x equals x squared x minus 1 cubed x plus 2. So this is your 57 in a textbook. Sketch the graph. So what is my A?
Is it 1?
1. Good. So that's larger than 0. And what's my n, the order of the polynomial?
6.
6. Even. So that will be the end behavior. And what are the roots? X equals what?
1 and
Well, you need to tell me
-2.
multiplicity every time you give me a root. So you said 1 with
Oh,
multiplicity?
1 and M3.
M3, good. Other root?
And then -2 M1.
Okay, another root?
0 M2.
Good. So I'm just gonna squeeze that in by moving everything this way. And then I'm going to pick this up and move it. Cool. All right, so now we have all three roots with their multiplicities. Let me check if it's 6. 2 plus 3 is 5 plus 1 is 6. Great. Your multiplicities better add up to exponents. I mean, that's where they came from, so. Cool. Let's see the graph. And I have 0, which is M2. I have 1, which is M3. And I have -2, which is M1. And I have this. So now we fit the graph, connect the dots. M1, pass through. M2, bounce off. M3, pass through. But you pass through as a cubic, which means it's a squiggle. There we go. And then connect up there. So this one over this pass through is like this. The M3 pass. The M1 pass is just straight through. M1 pass goes like this. M3 pass has the little squiggle like x cubed. And that's what we have. Okay. So we talked about the end behavior, talked about this. Let's see. Well, no, that's technically it. Yep, that's it. Any questions, concerns?
How do we? This has to do with polynomials, but we're like everything's separated into like parenthesis groups.
Well, your job is to factor them with any way you know. But we are going to have a special section when they're not separated like that, and when we have to do other stuff. That's going to be 2.5. So not all polynomials will be this nice. Generally, to put them in this form, you need to go and you need to factor. Maybe we can find a problem that would practice those a little bit. Well, there's plenty of them. I just skipped them. So problem 51. Let's see if you guys are able to factor this. I'm going to give you some time, but see if you can factor this. I'm going to go get a bottle of water, and you guys have fun with this. So factor graph, because once you factor, you will put in a form where you can do the m's, right, multiplicities and all that stuff. So let's see how well this works for you. I mean the algebra. I'll be right back. All right, let's take a look at some elementary algebra, which is factoring. So we put the polynomial in a descending order. That is rule number 1. Then we factor out the GCF, greatest common factor, which is in this case we can kick out negative x, and what's left is x to the 4th minus 6x squared plus 9. And now, since these two are perfect squares, we can try and use and see if it fits right with the middle term. Try and use the square of binomial, right? The a plus minus b, everything squared, is a squared plus minus 2ab plus b squared. So negative x, square root of the first, sine of the second, square root of the third squared, and then try the middle term, which is negative 6x squared. That's perfect. Okay, so that worked. And now, when we are here, we see that we have this x squared minus 3, which we can further factor, and we're going to get root 3, but that's okay. So negative x, and this becomes x minus root 3, x plus root 3, and it's still everything squared. So now by that rule of the power, right, with the a, b to the n equal a to the n, b to the n, which is another algebra rule, we get negative x minus root 3 squared, x plus root 3 squared. And we have everything we need. A is less than 0, right? It's negative 1. The n, we can just go and cheat off of the highest exponent, right? Because we had it that way. I mean, still you can count, right? 2, 4, 5, right? You can count the number of x's there, but we can just look at the basic one up there. So this is less than 0 and a 5, so it's going to look like this for the end behavior because it's odd. Odd, they look opposite way. And then when it's less than 0, it starts on the top left, sorry. X equals 0, multiplicity 1, that's for this guy. X equal root 3, multiplicity 2, that's this guy. And x equals negative square root of 3, multiplicity 2, which is this guy. Now we draw the graph and we're done. Zero, which is m1. And then these root 3s, since there are no other thing that's symmetric, you don't have to go and figure out exactly in a decimal or something. You just put them somewhere. So I used 4 boxes over here to the left and the right. Now I am aware that you might not be using proper paper for math, which is the square grid. So figure out the same distance on either side, whichever way you can on the line paper. And these two are both M2s. And then we have this behavior. So now the graph is set up and we just need to snake through the line. So bounce on M2, and you can also go and just do the bounce on the other one. And you say, oh, M1, straight through. Awesome. There we go. There it is. So we did the graph, right, of the function, and the best thing here is that you can go to the graphing utility or something and just you have the calculator. You can go to Desmos graphing on the internet, right? And you can graph this, and you will see that you get this shape. Now, how tall this peak is, that we'll need the calculus to figure those things out. Any other questions, concerns regarding this section?
No, it's pretty straightforward.
All right, awesome. So let me just recap in 2 seconds, and then obviously you can go back and watch it again on YouTube. But leading term test is the big deal here, and we start with the polynomial definition, understanding that highest power is your leading term, which is the biggest, largest exponent gives you the leading term. Then you have your x and y intercepts that you can compute, where x-intercept is actually your roots, which we were looking down by factoring and all that. Domain all real numbers. And the leading term test, where exponent gives us even or odd, and leading coefficient gives us this less than or larger than, which gives us this, right? And leading term test, right? This is the part that you will have to learn, right? And carry with you as you go through your years of mathematics later on. Polynomials tend to be the nastiest functions, actually, to factor and solve equations and so on. Everything else is easier. Exponential, logarithmic, trigonometric, like they all joke in comparison to polynomials. Polynomials are very nasty. We'll see that later for those roots. But when everything is factorable and nice, polynomials tend to be very, very friendly. And over here I gave you the quadratic formula and explained how these roots work. So when they actually go through x-axis, then you have a real roots, and those real roots, right? We're going to encounter complex roots later, right? In that 2.5, the roots are going to start jumping out as complex, and you will have to bounce them off in the air, not at the x-axis. But we'll deal with that when we get there. Multiplicity of the root tracks how many copies of the same root you have. So that's literally equal to the power of the term, of the factor. And the ways, I mean, this goes to M5, M6, M7, right? I just put the first 4 and what they look like, and then I told you that they get progressively wider, right, as you go. And a couple of these examples to reinforce this. So that's it for this lecture, and we're going to take a break. So bye.